Okay, final video on the standard basic DHSS model, and it's the third case, slide 6. The third case is basically slides 5 and 6. Yeah, this is slide 6, a limited resource, costless to extract, which is the standard DHSS case. And on the previous video we showed that if r dot over r is minus theta, then w r dot over wr is y dot over y minus r dot over r. Well, actually that applies, whatever. And then if this applies, we get this, that y dot over y is this expression from the land case minus beta over 1 minus alpha times theta. Super straightforward, actually, once you get the hang of it. But then now this is a little bit subtler. Okay. Yeah, of course this all applies on the balanced growth path, yeah. And you may not, at any given point, you may not be on a balanced growth path. If the capital quantity is wrong in relation to the other stuff, you may have to move towards balanced growth over time. You might want to bear that in mind, but we're interested in the long run in this course, and then we're assuming generally that we're on balanced growth paths the whole time. Assume perfect markets and symmetric equilibrium. What can we say about the resource price? Okay. So, I'm trying to remember if we went through this. Have we gone through this? Oh, there's no one out there. This is the Hoteling rule, right? Did we go through this? Oh shit, I don't think we've gone through this, have we? The Hoteling rule. Let me stop the video and have a think. Okay. I'm trying to remember in how much detail I should go through the Hoteling rule. I think I'm going to go through it superficially, very superficially. Okay. Which is all we really need for this course. We do it better in the biological resources course, or at least the methods you've learned there, you can do it super rigorously. And actually, yeah, there is an exercise where we do that. But what's the basic rule? We need to put ourselves in the position of somebody owning a stock of the resource. And this is one owner among many, so there are lots of rivals also owning stocks. Yeah. But here I am with my stock. My extraction costs are 0, and I'm just wondering when to open the tap, fill a bucket and sell it. Okay. What rate at which to sell a resource? And we can set this up as an optimization problem, but I think I'm gonna keep this super simple actually, and just wave my hands around. So basically, when we sell a unit of the resource, we get an income WR, don't we? WR times 1. Yeah, we sold 1 unit of the resource. So if we do that, we can stick this amount of money into the bank. And if we stick a unit of money into the bank, WR units of money into the bank, what is going to happen to our cash holdings, or our wealth? It's going to grow at a rate R, isn't it? The interest rate per year. So it's like if we call our wealth V, then V dot over V, if V is sort of the value of our assets, then the sort of current value of our assets, then V dot over V will be R. Yeah. If we take a unit of resource, and sell it and put the money in the bank. But if we keep that unit of resource here, how does its value change over time? It surely changes at this rate, doesn't it? The growth rate of the price of the resource. So if the price of the resource is growing fast, WR dot over WR is high, then our asset, this unit of oil, is growing rapidly in value. So if we have this portfolio management decision, where should we keep our assets? If this is growing, if the oil, a unit of oil as oil is growing faster in value than a unit of oil converted into money, then we'll keep it as oil. But if the money is growing faster, then we'll convert it to money. But these other owners are all the same as us, right? So that means if R is bigger than WR dot over WR, then all the resource owners are going to want to shift their entire stocks of resources into cash. Which means that the market, which we talked about here, is going to be flooded with oil. The oil price is going to nosedive. So that can't be an equilibrium, basically. Especially because the resource price will be instantaneously extremely low, from which point it will then rise incredibly fast because everyone will have run out of oil. But if the oil price then rises incredibly fast, we sell it, everyone sells, get nothing for it, and then immediately we see a massive rise in the oil price and we're absolutely kicking ourselves. So that can't be optimal, right? That can't be an equilibrium. But if WR dot over WR is bigger than R, then nobody wants to sell. Everyone wants to keep their assets in oil. Which means the price is going to go through the roof because nobody's selling. But this isn't a growth rate of the price, this is an instantaneous level of the price. And then everyone is going to want to sell, which is going to bring the price down really steeply, and again it's a contradiction. The only way we can get an equilibrium is when these two are equal. Returns to the different assets which are interchangeable must be equal. Yep, the returns to these interchangeable assets have to be equal for an equilibrium. And this is the Hotelling rule. Okay. So that's the Hotelling rule. That in an equilibrium, let's have a look at the slide again. Perfect market, symmetric equilibrium. What can we say about the resource price? This. Okay? The Hotelling rule. So let's put that together with what we had here. So then we can replace WR dot over WR with little r. So then we have little r is y dot over y plus minus r dot over r. Or, turning things around, r dot over r. Previously we just said, look, it's theta. But now we're dropping that because now it's endogenous. Yeah, we're working out r dot over r. R dot over r is y dot over y minus little r, which is no. And yeah, we wiped that theta, yeah, because we're now saying r dot over r is unknown. So we have plus, yeah, because r dot over r was minus theta, wasn't it? So now I can substitute from that for y dot over y, and then we have an equation just in r dot over r. That's our only unknown, isn't it? So we have r dot over r equals y dot over y, which is 1 minus beta over 1 minus alpha, times g plus beta over 1 minus alpha times r dot over r minus r. So again, take this over, usual kind of trick. It's so familiar, you know, the methods for these problems, they're so similar for the different varieties of the problem. So we have r dot over r times 1 minus beta over 1 minus alpha equals, so I've taken this over, yeah? So that's that. Now we divide by this and we get r dot over r is g minus r over 1 minus beta over 1 minus alpha. And this is less than 1, so this is less than 1, so this is bigger than 0. So the growth rate, oh right, yeah, and I should have said that. So in all these models, we generally assume that the interest rate is bigger than the growth rate. I'm not going to go into why that is, but there are very good reasons for that. Of course, in these crisis times lately, the interest rate, well, both interest rates and growth rates have been very low. The interest rate has often been, the short run risk-free interest rate has often been below the growth rate, but that is historically exceptional. Okay, so r is bigger than g, this is less than 1, so r over this is a lot bigger than g, so this is negative, yeah? This whole thing is negative, r dot over r is negative, r is declining, so the optimal path should look like this, which is the kind of thing we talked about before, yeah? R dot over r is negative, just like we had before when we said r dot over r is minus theta. And again, this is just parameters, so we know this. If we know our initial stock, which we could call S0, then we know this area has to be equal to this area, so we can decide the initial R. Okie doke. I'm just looking at this. I don't really know why I brought in the pure rate of time preference here. I guess it's just, yeah, the pure rate of time preference we would normally, I'm not sure I want to go into that, but this is the interest rate at the bank. The pure rate of time preference is the degree of impatience of households, and in very simple economies they're equal. But the interest rate of the bank we usually call R, the pure rate of time preference of households we usually call rho. So I guess this, I should have had rho, or you could, since they're equal, we could have had a rho here as well. Probably in the book there's some rows, I guess. Okay. Right, I'm just like trying to decide what to do. Maybe I'll just pause the video where I think Okay, I decided we're going to finish off this topic on this video. So I'm going on to slide 8, the Hartwig rule. So some of you might have heard of the Hartwig rule, which very sort of loosely and incorrectly interpreted is that if we invest resource rents in human-made capital, we'll be guaranteed sustainability. So remember, there's no costs of extraction and there's perfect markets. So the price of the resource, which I call WR, is pure resource rent. And according to the simplified and incorrect interpretation of the Hartwig rule, if we just take the income from selling these resources and invest that in new machines, we will get sustainability. That is unfortunately utter nonsense. Okay, you can set up economies in which it's true, model economies, but in general model economies it's not true. A trivial way to see that is that if human-made capital depreciates over time, whereas this never depreciates, it's only used up, then clearly if you convert this into human-made capital, but then the human-made capital starts depreciating and this is running out, you're done for, aren't you? You can't possibly maintain a stable level of income. Your income is going to approach zero. If a positive flow of this is essential, I'll say this is all without technological change. Yeah, the Hartwig rule is all in situations where G is zero. Okay. Can we have sustainable consumption just based on exchanging resources for capital? In economies where capital depreciates over time, the answer is forget it. Okay. So that's kind of just there's been a lot of attention paid to the Hartwig rule historically. So it's just in case you've seen stuff about the Hartwig rule or whatever, I just want to mention that, but it's not super important in the course. Much more important in the course is slide 10, historical data. So what does the historical data show? I'm going to pause the video and clean up the board here. Okay, so what does the data show? Well, what do the models show? Log scale time. So the land model, well, that showed that R is constant, didn't it? Y is going to grow at the growth rate of productivity with a little penalty from the beta, and the price of land will track Y. The abundant costly model, what did that show? That showed slightly steeper growth in Y. R tracks Y and WR is constant. And the Hoteling model, if you like, the third one, what did that show? That shows a slower growth in Y, a very steep rise in resource prices, and a decline on a log scale in resource use. How do these match up to the data on, for instance, global metals, global energy? Have a look at the graphs. Pause the video if you're in any doubt whatsoever. They match this one. How does the data on land prices and land quantity match? Well, reasonably well. not brilliant actually, but well, it's tricky to find good data on land prices. I have looked at this, but it's a reasonable match to this. Okay, so these two models do a reasonable job of matching very broad basic data. This model is a total disaster, right? It's completely and utterly wrong. It's not reflecting reality, which either suggests that the limits to growth people were right and we're just on a completely crazy, irrational path and going to go over the cliff, or there's something horribly wrong with this model. Okay, and it turns out there's something horribly wrong with this model. Okay, we might be irrational too. That remains to be. Of course, we're not perfectly rational. To what extent are we making crazy decisions? That is an open question. But this model is definitely horribly wrong. Okay. What to say? I was just thinking, shall I say more about that? Like, could it be that we are this irrational? Okay. I mean, there's enormous money to be made in these industries, extraction industries. Okay, and we know there are property rights, either private property rights for firms or where countries are in control. The country effectively has property rights over its own resources. Oh God, I'm getting. Need to put the flight mode on. Sorry, I lost my track now. Yeah, there's enormous money made in these industries. If we were on an irrational path, there would be incredible amounts of money to be made by doing the rational thing. And you would beat the market, right, by predicting. Because if and when this ever happens, or if we start getting close to this and people realize, the price of resources is going to absolutely rocket. Okay. Because if this is correct, it's basically saying that the prices of resources which are staying fairly constant are totally sort of wrong. They should be much higher and growing steeply. If you realize this, you will conserve your resources today to earn incredible profits in the future, right? Okay. So it's very unlikely that we are this irrational, or that resource owners are this irrational. And on the other hand, it's quite easy to see that this model is completely wrong, okay, in critical respects. Yes, resources are limited, but no, they are not zero extraction costs. That is the key. Okay, we need to think about extraction costs much more carefully to get closer to this model, where we had abundant resources but costly, and that did much better on matching the data. So we need to think about this model and adding limited stocks to this model to see what happens, and that's what we're going to do in the next video.